We're going to talk about the dependent samples t-test here. Well, in independent samples, observations are not linked as pairs. On the other hand, when two samples are dependent or paired, observations are linked. So, some examples of dependent samples would be pre-test and post-test samples. So the pre-test measurement is the measurement prior to an intervention. The post-test measurement is that subsequent. So a group takes a measurement at pre-test time. That's, so to speak, sample 1. That very same group of people takes the same measure again after the intervention has finished. That is the post-test, and that's sample 2, and your pre-test and post-test samples are dependent. If you were doing a study of partners in relationship, so that you had, for instance, wives in sample 1 and their husbands in sample 2, and you might be studying, for instance, communication in relationship and having a measure that measured wives' opinions, and then that same measure for the husbands. So the husbands and the wives there are paired. So if the wives are sample 1 and the husbands are sample 2, the observations in each of those sets of samples are not independent observations, but instead you've got paired samples. If you were studying sisters and brothers, and perhaps you want to determine, well, who tends to get better grades, sisters or brothers? So if you had sisters in one sample and the brothers of those sisters in a second sample, then you would have paired observations and you would have paired samples. So Chapter 12 presented the independence of observations assumption, which is an assumption for the significance procedures that we're covering in this text. And the independence of observations assumption is, in essence, that the observations of each person are independent of those of each other person. As if, for instance, you flip a coin one time, you flip a coin the second time. How you flip the first time doesn't influence how you flip the second time. In other words, whether you get heads or tails on the first flip has no bearing on the second flip. So you've got independence. But when you get the linkage and the pairing, and when you get dependent observations, the independence of observations often does not hold. So when the independence of observations doesn't hold, as for instance in dependent samples, you cannot carry out an independent samples t-test. Though the independence of observations assumption doesn't hold in paired samples for each individual observation, it does hold for the pairs of observations. So in other words, if we have our sample, for instance, of wives and husbands, the responses or measurements on the first pair of spouses has no relationship to that on the second pair and the third pair. What each pair responds is independent of what each other pair responds. So the independence of observations, though it doesn't hold for the individual observations, it does hold in paired samples for the pairs of observations, and thus you can indeed carry out a dependent samples t-test. So the dependent samples t-test is used with dependent samples. Now, when you have dependent samples, it's often the case that there is positive correlation between scores, which is to say, for instance, if a wife in a given dyad, if she's positive regarding communication, then our best guess is that her husband will also be positive. And if in another relationship the wife is very negative, our best guess is probably that the husband in that relationship is too. So oftentimes when you get paired samples, what you have is positive correlation between the scores in the two samples. Now, if you get strong positive correlation between the two samples, then you can get a substantial increase in power. And I should be more explicit and say if you get strong positive correlation. But the correlation indeed is often positive and sometimes strongly so. Now think about pretest and post-test scores. Pretest and post-test scores often have strong positive correlation. And therefore, measuring both pretest and post-test scores and including them in analysis often increases your power. But to give you an intuitive feel for this, you have a group of people in therapy for depression. You take pretest scores on a depression measure. Those scores become sample 1. The intervention is delivered. You take post-test scores. These become sample 2. Now we hope that the therapy has worked and that overall we're seeing a decrease in depression scores from sample 1 to sample 2. But the positive correlation between depression scores is such that if Johnny is very depressed at time 1, it may well be that he will be among the most depressed persons at sample 2. I mean, perhaps his depression has decreased, but perhaps that's been the case for many people in the sample. Now then, if Sarah has a very low level of depression at time 1, other things being equal, if there's positive correlation, which is what we suspect there would be, since she was among the less depressed at time 1, we think she'll be among the less depressed at time 2. So in sum, with pretest, post-test samples, we often see strong positive correlation between scores, and there often is more power than one would think simply based on the number of pairs or the numbers in the sample. Now, the hypothesis pairs for the dependent samples t-test are exactly the same as those for the independent samples t-test. And with the non-directional pair, you have a two-tailed test. With the directional pair, the test is one-tailed. Degrees of freedom equal n minus 1, where n conveys the number of pairs. And here are some guidelines for when results will be sufficiently accurate. And again, the n here is conveying the number of pairs. So if n is 10 or greater and you have less than strong skew, in other words, moderate or modest skew or no skew at all, then you should get accurate results. If sample size is at least 20, then results will be fairly accurate, providing that you don't have extreme skew. And if n is greater than or equal to 60, then you really don't need to be concerned about any effects of skewness on accuracy. You'll get reasonably accurate or really quite accurate p-values regardless of skew. So let's do an example to demonstrate the increase in power that comes from a positive correlation between pairs of scores. Now suppose that you had the data presented at the top of this slide, and let's say this data pertains to the number of times that parents nag a child. So we have n equals 16 people in both groups. The mean is 27 nags in group 1, which means the same thing as sample 1, and 22 nags in group 2. Here are the standard deviations. The standard deviation is 11 in group 2 and 6 in group 1. So the standard deviation is larger in the second group. Let's presume that skew is moderate in both of these samples. Our sample size is greater than 10, the skew is moderate, so our p-values are going to be sufficiently accurate. And what we have here is presumably a design in which sample 1 receives no intervention and sample 2 does indeed receive an intervention. So these are two different treatment groups, so to speak. Now think about these groups. Those in sample 1 have nothing in common with those in sample 2 in terms of things like they're not brothers and sisters, they're not linked in some way. This isn't a pre-test, post-test situation. We've got two different samples. Since the scores are not linked, the samples are independent, and the independent samples t-test is the appropriate test to use. Estimate of the standard error of the mean in this situation comes out to be 3.13. I don't show this calculation. You don't need to be able to do that calculation. Here's our calculation of t, and I make note at the bottom we're using the unequal variances formula. E equals 1.60. Presuming that we've got a non-directional pair and a two-tailed test, this t does not have an absolute value that is sufficient for rejecting the null. So we will fail to reject the null. Now I'm presenting identical data on the number of nags, so to speak, in this new slide. Now the difference is that in this new slide, sample 1 is conveying pre-test scores and sample 2 is conveying post-test scores. I'm going to presume that I carry out the calculation of the correlation between the pre-test scores and the post-test scores, and that correlation comes out to be 0.70, indicative of strong positive correlation. These two samples are paired samples. The scores are linked. If we have, for instance, Cindy in sample 1, we have Cindy's pre-test score in sample 1, and we have Cindy's post-test score in sample 2. So there's the linkage. These are dependent samples, and therefore we should carry out the dependent samples t-test. Positive correlation between scores in the two samples has the effect of making the denominator of the t-test smaller. It makes the estimate of the standard error of the difference between means smaller. And so in this case, that calculates to be 2.01. Now let's go ahead and calculate t. So again, we have the same means in sample 1 and sample 2 as we did in our prior example, but now we're dividing by 2.01 rather than by 3.13, the positive correlation having made this denominator smaller. So t calculates to 2.49, and I don't show it, but we could go and consult the table of t-test values, and the absolute value of 2.49, which is indeed 2.49, that is indeed large enough for us to reject the null at the 0.05 level. So what's been demonstrated again is that positive correlation between samples can markedly increase your power. And this is not a course on research design, but as a general strategy, it is a good idea to get pre-test data and post-test data if you can. In essence, when you carry out a dependent samples t-test or other related procedures, I mean, in essence, you are basically controlling for noise that relates to the pre-test situation, and you control for that noise. You take it out of the equation. You, so to speak, build a smaller haystack, and you increase your power. Also, in some other studies, including pretest data can reduce bias that would otherwise be present.